Today we are going to initiate some discussions on vibrations of membranes. So, today first we are going to look at the dynamic modeling of membranes. Now, to begin with, what are membranes? A membrane is a two-dimensional elastic continuum which cannot resist or transmit bending moment. Now, when we discussed about strings, the string was a one-dimensional elastic continuum which does not resist bending moment, but now this is membrane is a two-dimensional elastic continuum, but then there are some fundamental differences between a string and a membrane, which means that a membrane is not just a two-dimensional extension of a string. So, let us first in order to start our dynamic modeling, let us first enumerate our assumptions that we make for the modeling, mathematical modeling of membranes. So, first of all, we where do we find membranes? We find membranes in eardrums, on drum heads, and in certain kinds of microphones. Etc. Now, we study membranes not just to study drum heads or eardrum or microphones, but to understand this two-dimensional elastic continuum, which is the simplest of its kind, because it does not transmit bending moment. Now, in order to model membranes, we will assume that the membrane is flat, and the deflection is purely transverse. So, when you have let us say an inflated membrane, let us say a balloon, in that case the dynamics is more complicated, because the deflection can no longer be considered to be just transverse. There is a coupling between the transverse and the in plane modes. So, we are going to make this assumption that our membrane that we analyze is flat, so that the only we have to consider the transverse deflection of the membrane. The second assumption we make is that the slopes are small, so if the deflection is so you have a certain deflection, then by small slope you can imagine that the maximum deflection divided by the characteristic dimension of the membrane. So, suppose I have a membrane of, let us say, this size, then the transverse deflection should be much smaller than this dimension or this dimension of the membrane. So, slopes should be small. We assume that the tension does not, so tension is uniform, and it does not change with deflection. So, it is constant, it does not change with the deflection. and finally, we also assume that the thickness does not change. So, under these assumptions we are going to now look at the modeling of a membrane. So, let me first draw an infinitesimal element of this membrane. So, here we have I have considered an element of this membrane which was initially flat on the x y plane. So, we have, in order to locate the membrane, we consider this field variable w, which is a function of now x, y and time. So, here we have these forces. So, I have taken a little element of the membrane and I will draw the free body diagram. So, if this point is x y, I will denote this as the force on this this edge as T, so here I have, so this is dx and this is dy. Similarly, the force on this edge is T x y t, so these are the forces acting on this little element. Now, here this T is the force per unit length. So, you can think in this way that there will be stresses on this cut. So, if you integrate this stress over the thickness, then you obtain this T, which is force per unit length. So, stress integrated over the thickness of the membrane is force per unit length. So, some kind of a resultant, stress resultant. Using this, we are now going to write down the equation of motion. So, let me consider this little element. So, the transverse dynamics So, let mu be the mass per unit area. So, mu is the mass per unit area. So, the area of this element may be written as mu times dx into dy. So, that is the mass of this little element times the acceleration in the transverse direction, that must be equal to the net force in the transverse direction. So, I can write, so this is, so this T is the force per unit length of the cut now, because it has been integrated over the thickness. So, it is equal to the force per unit length of the cut. So, for example, the force because of this on this face is T times dy, because the length of this face is dy. So, that is a force, but it must have a so I must take a component which is in the transverse direction. So, that component, so if this angle let us say is phi, then I must have sine so I must take sine of phi to find out the component of this force in the transverse direction. Now, sine of phi is approximately equal to tan of phi, and that is equal to del w del x. So, to find out the transverse force because of this, I will use del w del x at x plus dx and y, and of course, at time t, and on this side it would be del w del x at x y, and similarly from these two edges. So, this T dx is the force, so since we are assuming that the tension in the membrane is uniform, so it is essentially isotropic, it is homogeneous. So, everywhere it is T, though I have written it like this to indicate that this vector might be different. So, magnitude wise it is the same. So, here it is del w del y is in this direction, it is del w del y. So, this must be the equation of this must lead us to the equation of transverse dynamics. So, if you divide throughout by dx dy and make some simplifications. So, this so del w del x at x plus dx. So, let me write this down. So, del w del x x plus dx comma y may be written as and so on. So, I can have an expansion, a Taylor series expansion of del w del x at x plus dx comma y in terms of del w del x at x y and del w del x and its higher derivatives at x y. So, using this expansion here, I can therefore finally write this as so, from this will contribute a term del square w del x square, and this is going to contribute the term del square w del y square. So, that implies now this is the Laplacian of w. And this can also be written as where this C is once again looking at the structure of this equation and the dimension of this quantity. So, this is this has a dimension of speed. So, this is the speed of transverse waves in the membrane. So, this is the transverse wave speed in the membrane. So, this is the structure of equation for transverse vibration of a membrane. Now, you see that here we have double derivative in x as well as y. So, we would require boundary conditions on these edges. So, let us look at the boundary conditions. So, if you have let us say rectangular membrane, please note one more thing, that we have derived the equation considering the Cartesian coordinate system. We will look at the general situation in a moment. So, if you have this x y plane and a flat rectangular membrane, then if this is fixed on these edges, then we can easily write the boundary conditions. So, at x equal to 0, that would mean this face, and for all of y and for all time this is fixed. Similarly, on this face we would have w at x equal to a and all of y, and for all time this must be 0. On this edge, for all of x and y equal to 0, this must be 0, and on this edge so when the edges are fixed, then you have 0 displacement. There is another possibility where you can have sliding edge. So, in a sliding edge, the membrane can so it's very similar to the sliding edge of a string. So, if you have an edge of a membrane which can slide, in that case the condition at this boundary, let us say at x equal to a, it is very similar to that of the string. So, tension times the force per unit length times the slope, that must be 0. So, this is the force per unit length at this edge. So, the whole thing is so this is the tension in the membrane, the force per unit length so we must take the transverse component of this force. So, that is determined by taking the multiplying it with the derivative of w with respect to x, as we have seen. So, that must be 0 for a sliding boundary. Now, when we go to the polar coordinates, we use polar coordinates when we have a circular membrane. So, suppose you have a circular membrane of radius a, then first of all the equation of motion for this membrane. So, we have the equation of motion for a rectangular membrane written out in this form. So, we consider we can derive the equation for a circular membrane from this by a simple coordinate transformation. So, if you consider that the radial coordinate r is square root of x square plus y square and phi is tan inverse y over x. So, using this you can derive these operators del x in terms of derivative with respect to the radial and the angular coordinate. So, if you use these transformed operators, then finally you can get the equation of motion in the polar coordinates. So, these are obtained, this is obtained as where now W, the field variable, is a function of r, phi and t, and for a fixed boundary we have so the boundary condition is quite simple. Now, this choice of coordinates actually is guided by the boundary. So, for simple boundaries like a rectangular membrane or a circular membrane, the choice is very clear, but for other shapes, some of which we are going to discuss later on, we will see how they are dealt with. So, so here we have discussed about right now about the Newtonian formulation. Let us also look at the variational formulation. So, the variational formulation for the dynamics of membranes. Once again, I mean to motivate, so the variational formulation is quite powerful. Not only it gives us the equation of motion, but also the boundary conditions, and even more important than that, it gives us methods by which we can solve the or discretize the dynamics of continuous systems. For example, we have looked at Ritz method. So, for that reason we must also discuss the variational formulation for the membranes. Now, to begin with, we write down the kinetic energy expression of a membrane. So, if W is our field variable, then half, so we have considered mu as the mass per unit area. So, mu times dA is the mass of a little element of the membrane. So, half mass times velocity square, and this when we integrate over the area of the membrane, we are going to get the total kinetic energy of the membrane. Next, we would like to find out the potential energy when the membrane deflects. So, to determine the potential energy, we have considered that the force per unit length, the tension in the membrane, the stretch in the membrane. So, that remains almost constant, it does not change. So, if you think about it in this way, that the stress and the strain, if the stress in a material, because if stress remains fixed, only then the force per unit length, which is determined by integrating the stress, so that must also be constant because T is fixed. So, the energy per unit volume is given by the area under this. So, it must be this sigma in the x times epsilon in the x plus sigma in the y times the epsilon in the y. So, this is per unit volume. So, you must integrate this over the volume. So, first over the thickness, and then over the area of the membrane. So, xi is along the thickness direction. Now, this stress, so this is taken almost uniform over the thickness. So, this turns out to be sigma into h. So, sigma is T over h, and in both directions it is the same. Now, the strain, we have seen from the case of the string, the strain is half of del w del x whole square. So, in the other direction as well, we must have now. So, therefore, finally, when you substitute all these expressions in here, so this is what you will get. Now, this can be written as in a coordinate independent manner. We can write this where this delta is for the Cartesian so this is the gradient of this field variable, the magnitude square of that vector, the gradient of the field variable. Now, so this is the potential energy. So, finally, our Lagrangian So, that is a Lagrangian, and from Hamilton's principle we can write so this must vanish. So, the variation of the action integral, which is the integral over time of the Lagrangian between two time points, so that variation must vanish. So, if you consider this Lagrangian and take the variation, now here I have used this property that the variational operator commutes with the gradient operator. Now, this term I will integrate by parts with respect to time once, now for this term let me so this term, in order to simplify this term, let us look at this identity. So, I am taking the divergence of a vector. So, this is a vector and this is a scalar. So, it is a scalar multiplied by a vector, and we know that this turns out to be so. So, this is the gradient of the scalar dot the vector, and so this is the divergence of this vector. Now, so therefore, I can use this here to rewrite this left hand side. Now, this term goes to 0 because at t 1 and t 2 there cannot be any variation. So, what I am then left with is So, this goes on this side. So, this comes with a positive and this is the Laplacian. So, this must vanish. So, then now here I have the divergence of a vector quantity. So, here I can use the Gauss divergence theorem. So, which says that so the divergence of any vector over this area integrated must be equal to vector dot the normal to the boundary. So, integrated over the boundary. So, if you use this here, then we have a boundary term arising out of this, which so this integral over this area of this term, that gives us this boundary integral dot the normal to the boundary Now, once again we apply the argument that the variation over the boundary and over the domain are independent. So, therefore, we obtain directly from here the equation of transverse dynamics that we had obtained before. And now, we have from this this boundary term, we obtain the boundary conditions. So, we must have so this calculated at the boundary, of course. This is sometimes written as so is the normal derivative. So, gradient dot the unit normal at the boundary is the derivative along the normal to the boundary. So, this is a this boundary condition is a natural boundary condition whereas this is a geometric boundary condition. Now, let us consider this example. So, if you have, for example, a rectangular membrane. So, the unit normal at the boundaries let us say this. So, let us understand this the natural boundary condition which says so, for example, at this boundary, at the right boundary at x equal to a. So, n is 1 0. So, therefore, at the right boundary you have this condition. If it is a dynamic natural boundary condition. If the boundary is fixed, then of course, you have the geometric boundary condition which says that the displacement is 0. Now, just briefly let us look at the polar coordinates. So, the Lagrangian in the polar coordinates may be written as so in the case of let us say a circular membrane, you have the kinetic energy and the potential energy, and of course, there is a 1/2. Now, so in the general case, suppose you have an arbitrary boundary. So, here so if you have an arbitrary membrane, then you can so this is the boundary. You can represent the unit normal ds, and then the boundary conditions for an arbitrary boundary can be written in terms of more general coordinate free notation. So, finally, you have in the coordinate free notation the equation of motion So, corresponding to, for example, the Cartesian coordinates, this is nothing but and for the polar coordinates, so this is the operator, and the boundary conditions in can be written like this. So, this is the general representation of the equation of motion of a flat membrane which is undergoing transverse vibrations. So, to conclude, we looked at the dynamics of membranes both from the Newtonian as well as from the variational perspective. In the following lectures, we are going to study the vibrations of membranes with circular and rectangular shapes. So, with that we conclude this lecture.